There may be another version of you, not a spiritual twin, not a metaphor, not a thought experiment wearing a costume. A real person, built from the same kind of atoms, standing inside the same physics the rest of us answer to. In the gentlest version, that person is you down to the last detail. Make it slightly stranger, and they match you in everything but one choice from this morning, a left turn where you went right. Stranger still, they carry your name across a life you never came close to living. None of this starts in science fiction. It falls out of equations physicists use every day and mostly try not to stare at directly. If the universe really keeps all of them, which one gets to be the real you? Start with the rule itself, the one equation that fixes how anything quantum changes from one instant to the next. Physicists have pushed it for nearly a century against every system they could build, and it has never once handed back a wrong number. It is also smooth in a way that should unsettle you more than it usually does. Feed it a particle that could pass to the left or the right of a barrier, and it does not select. It carries both possibilities forward at once, each with its own weight, neither erased, and it keeps doing this for as long as nothing interrupts it. The reason this is more than bookkeeping is that the path you never see leaves fingerprints on the path you do. Fire particles one at a time at a screen behind a barrier with two narrow openings, slow enough that only one is ever in flight, and each lands as a single point of impact, so each one clearly went somewhere definite. Let the points pile up over hours and they sort themselves into bands, bright stripes split by dark gaps where almost nothing arrives. A single particle crossing a single opening has nothing to combine with and leaves a plain smear. The striping can only form if each particle somehow sampled both openings and the two versions of its journey overlapped, adding up in some places and canceling in others. The version that took the opening you would swear it missed pushed on the version that took the one it used. Saying a particle could go either way sounds like ordinary not knowing, the way a covered coin is already heads or tails and you simply have not looked yet. The dark bands kill that reading. If each particle were secretly committed to one opening the whole time, the screen would show two plain smears laid on top of each other, never stripes. The canceling demands that both routes be live at the same moment, not one route hidden from you. Superposition is not a statement about your ignorance of the particle. It is a statement about the particle. The canceling itself is what breaks intuition hardest. Two ways of arriving can add up to less than either one alone, down to nothing at all in the dark bands. The way two water waves meeting crest to trough flatten the surface where they cross. Electrons do it, light does it, whole molecules do it, and the flattening is exact. The water picture carries you to the door and then fails, because a water wave is built from trillions of molecules sharing the work, and a single electron is not built from anything smaller, arriving in pieces. One indivisible thing interferes with itself. And the only way that happens is if both paths were really open, held by the same smooth rule, right until they met on the screen. Then change one thing, and change almost nothing. Set a detector at the openings that records only which one each particle uses. No push, no block, just a registration of the route. When that record exists, the stripes vanish, and the particles stack into two plain mounds behind the two openings, exactly as marbles fired through two gaps would pile. You did not close a path. You only made the world hold which one, and the holding flattened the interference into two dull heaps. For most of the last century, physicists closed the gap between the two-path rule and the single mounds with a second rule bolted on beside the first. The equation runs along, holding every possibility at its proper weight, right up until someone measures, and at that instant, every possibility but one is struck out, a lone survivor chosen at random, and the rest stop existing. The arithmetic is flawless. Every laboratory result for 100 years, sits inside its predictions to as many decimal places as anyone has bothered to check. But look hard at what it asks you to swallow. Reality obeys one law almost always, then a completely different law for an instant, whenever an observation happens, with no statement anywhere of when that instant falls or what counts as an observation. Physicists even named the boundary where open possibility is supposed to snap into one fixed fact. They called it the cut. The trouble is that no experiment has ever caught the cut sitting at any particular place. You can describe the particle quantum mechanically, or fold the whole instrument into the quantum description as well, or carry it further and include the body of the person reading the result, pushing the boundary higher up the chain each time, and the predictions come out identical no matter how far you push it. A boundary that can sit anywhere along the chain and be found nowhere in it behaves less like a physical event than like a placeholder standing in for one. Collapse was never derived from the smooth equation. It was bolted on as a separate postulate in the 1920s for the single purpose of forcing the theory to match the lone outcomes people kept seeing. A smaller group took the opposite repair. Rather than delete the collapse, they tried to make it physical, writing a real random jump into the equation so that large objects collapse on their own, with nobody watching. Those objective collapse models are testable, and experiments keep shrinking the room they can hide in, yet none has been confirmed, and the plain equation keeps passing untouched. The field is split, and the split is honest, because the evidence so far cannot tell the repairs apart. In 1957, a graduate student at Princeton named Hugh Everett leaned on the question, what if there is no second rule? What if nothing is ever struck out, and the smooth equation means precisely what it says all the way down? Then the outcomes you fail to see are not destroyed at the moment of looking. They continue, carried by the same law, still real, only no longer reachable from where you happen to stand. The particle goes both ways. The detector reads both values, and the person watching the detector ends up in two versions, each one certain that a single definite thing occurred. Neither version is a copy stamped from an original, and neither is a ghost of the other. Both are made of the same matter, obeying the same equation, the way a single beam of light striking a half-silvered mirror departs as two beams at once, one passing straight through and one reflecting away, each a real continuation of the light that arrived, and neither a duplicate of the other. The branching person is that same split scaled up, one configuration of matter becoming two, both carrying the past forward, with no copy made anywhere in the process. Everett's move costs nothing in new physics. He added no force, no particle, no dimension. He removed something, the second rule, and let the first one stand alone, and everything collapse predicted his version predicts too, because the weights the equation hands each branch are the same weights collapse used to pick its winner. So the door this whole night walks through opens right here, on a rule that refuses to choose and a patch that chooses for it without ever saying how. If the loser of every quantum coin toss keeps going somewhere with a version of you inside it, the next thing to understand is why that blur never reaches your senses. Why does the world arrive already settled into one outcome when the law beneath it is still holding all of them? A particle can hold two states at once, and you are made of particles, and still you have never caught yourself holding two states at once. The sharp form of the puzzle is not that superposition is strange. It is why superposition stops at your scale, why the world delivers one outcome so dependably that the blur underneath stayed hidden until people built instruments fine enough to trap it. The account that came together across the 1970s and 80s carries the name Decoherence, and the surprise folded inside it is that it needs no collapse, no second rule, no special role for a conscious watcher. It needs only the fact that nothing quantum is ever truly alone. A particle in two states does not stay sealed in those two states for long. It touches its surroundings, and the instant it does, the surroundings record where it is. An air molecule rebounds off it at a slightly different angle depending on its position. A passing photon scatters differently. The two versions of the particle stamp two different imprints onto everything they brush against. That stamping is what kills interference, through the same mechanism that erased the stripes when a witch-path detector switched on at the slits. To recover the dark bands, the two paths have to meet and overlap cleanly. Once the information about which path was taken has been smeared across thousands, then billions, then uncountable particles of the environment, restoring that clean overlap would mean gathering every one of those particles and steering it back into perfect step at the same instant. The branches were never destroyed. They were made orthogonal, the exact word for two possibilities that can no longer reach across and affect each other, because every channel they once shared now points a different way. The speed of this is what undoes intuition. For a single electron held carefully in a vacuum, the separation can be slowed and even partly reversed, which is the whole trick behind a quantum computer. For a dust grain drifting through ordinary air, the calculation runs the other direction completely. The branches separate in something near a 10 millionth of a trillionth of a second, faster than light crosses the width of a single atom. By the time the quickest detector you could build has so much as twitched, the parting is already old beyond any hope of recovery. This is the reason you feel single. The entanglement that hides your other branches is happening inside your own body, billions of times faster than a nerve could ever fire. The boundary is not fixed by size in any simple way, and the lab has been dragging it outward for 3 decades. In 1999, a group in Vienna sent buckyballs, soccer ball molecules of 60 carbon atoms each, through a version of the two-opening setup and recovered the interference bands, proving that an object of that size still travels both ways when kept isolated enough. Since then, the same has been done with molecules of hundreds and then thousands of atoms. Every step up is a fight against decoherence, a question of how completely you can stop the molecule from telling the surrounding air where it is. The classical world is not a separate kingdom from the quantum one. It is the quantum world, with its witch-path information leaking out too fast to catch. A quantum computer is the same fight run on purpose. It holds a handful of particles in overlapping branches long enough to let them interfere before the environment notices, and its deadliest enemy is the very leak that seals you off from your other selves. One stray vibration, one warm photon, and the branches decohere. The computation slumps into ordinary noise, and the engineers begin again. The entire craft comes down to buying a few more microseconds of isolation. The equation by itself does not say which states get to be the definite ones. You can write a superposition of a thing here and the same thing there, or you can rewrite that identical situation as a superposition of two bizarre blends, here plus there and here minus there, with equal mathematical right. Nothing in the bare equation prefers the first description, yet the world only ever serves you the first. Pointers rest at one reading, never at a ghostly sum of 2. The reason the environment settles this is that air and light and heat all interact with objects according to where they are. So position is the property that gets copied outward and locked in, while the strange blends smear instantly and never survive to be seen. The world looks solid. Along exactly the axis the environment keeps measuring. For a while this looked like the entire answer, and the elegance of it is real. No magic, no observer, no line where physics changes its mind, only ordinary entanglement running faster than thought. The first time I worked through it, I was sure the measurement problem had quietly dissolved. It had not. Decoherence explains why the branches stop interfering and why each one looks classical from inside. It does not explain why there is a single outcome you find yourself living rather than the whole branching structure at once. It tells you the branches are separate and stable. It does not tell you why you are in this one. To reach that, decoherence quietly borrows the idea that the branches carry probabilities, that some are likelier to be your branch than others. And where those probabilities come from, Why they take the precise values a century of experiments confirm is the crack the smooth equation has never sealed. So the world arrives single because your branch lost contact with its siblings in less time than light needs to cross an atom, walled off by the same tangling that makes you a stable object at all. The branches are real, separated, and quietly weighted, some of them thick and some vanishingly thin. If every outcome happens in some branch, the cleanest guess is that they should all count the same, one world each, share and share alike. The experiments say otherwise, and they say it sharply. Why should branches that all equally happen not all equally count? If every outcome happens in some branch, the honest expectation is that each should weigh the same. One world per result. A flat tally. Quantum mechanics refuses that tally, and it refuses with a precision that has never once slipped. Build a measurement rigged to land one way 99 times out of 100, run it across millions of trials, and the long-run frequencies settle on 99 and 1 to as many decimals as your patience allows. Both outcomes branch. Both are equally real in Everett's account. They simply do not arrive equally often, and the rule that fixes how often is the single strangest line in all of physics. The rule says the probability of an outcome is not the size of its slice of the equation but the square of that size. A branch carrying half the amplitude does not show up half the time. It shows up a quarter of the time, because 1/2 squared is 1/4. That exponent, that small 2, is the one place randomness enters the whole of quantum theory. Take it out, and everything left is rigidly deterministic, the smooth equation grinding forward with no dice anywhere. The squaring is where the certainty of the law turns into the chanciness of the world, and nobody set it there for a reason anyone can point to. It is forced by the shape of the theory, where amplitudes are not plain numbers but carry a direction as well as a size, and only the squaring lets those directions combine into the interference the slits actually produce, while the final count comes out real and never negative. You can even ask whether the exponent is exactly 2 or merely close to it. In 2010, a group sent light through 3 slits rather than 2 and hunted for a kind of interference that could only appear if probability built up in a more tangled way than a clean square permits. They found none, down to a few parts in 100. The exponent is 2, not a hair above or below, and the world has been checked for the difference. Max Born wrote the rule down in 1926. And the way he wrote it shows how little it was grasped at the time. In the body of his paper, he proposed that probability track the amplitude itself. Then, in a correction added to the proofs, almost in passing, he changed it to the square. He had the right rule and no derivation, only the brute fact that the squared version matched experiment and the plain one did not. A footnote fixed the most accurate predictive rule in science, and 100 years on, we are still arguing about why the footnote is true. The first serious attempt to make the squaring less arbitrary came from Andrew Gleason in 1957, the same year Everett published. Gleason proved something sharp. If you insist only that probabilities attach consistently to the outcomes of measurements, and you work in a space of 3 dimensions or more, then the squared rule is not one option among many. It is the only assignment that holds together. Gleason began by allowing that there are probabilities to assign at all. He derived their shape, never their existence, and in a world where every outcome genuinely occurs, the existence of probability is the exact thing in doubt. The Everett picture runs straight into a wall here, and the wall is built out of the word probability itself. In an ordinary account, probability measures your ignorance of which single thing will happen. In the branching account, nothing is uncertain in that way. Every result happens, each in its own branch, each witnessed by a version of you fully certain it occurred. So, before a measurement, what could it mean to call one outcome more probable than another when you are guaranteed to live through all of them? This is the incoherence problem, and for years it looked like it might sink the interpretation outright. The repair turns on, changing what the uncertainty is about. You are not unsure whether an outcome will happen. You are unsure which of the resulting people you are about to be. In the instant after the branch forms and before you read the result, there are already two of you, matched up to that moment, each sitting in a different outcome, and neither yet knows which one it is. That ignorance is real, and it is ignorance of self-location, of which copy holds this particular point of view. Charles Sebens and Sean Carroll built this into a derivation in the last decade, showing that a person caught in that brief not knowing, reasoning consistently, is driven to assign credences that obey the squared rule. A separate road reaches the same place from action rather than belief. David Deutsch argued, and David Wallace worked out in detail, that you need not mention probability to begin at all. Take someone who accepts that the world branches and who places bets on quantum outcomes and demand only that the betting stay consistent, that they never accept two deals which together lock in a loss. From those bare requirements, the squared weights fall out as the only stakes a coherent gambler can hold. The startling part is which way the logic runs. Probability is not assumed and then measured. It is manufactured out of consistency alone, the way arithmetic forces a sum whether or not anyone wanted that answer. Wojciech Zurek found a third path, pulling the rule from a symmetry hidden inside entangled states, with no appeal to betting or belief. Three independent derivations, from probability theory, from the logic of choice, from symmetry, all landing on the same exponent. When that many separate roads end at one address, it grows hard to keep calling the address a coincidence. And still the matter is not closed, and the people keeping it open are not cranks. Each derivation must assume something before it can move, a notion of rational preference, a measure across the branches, a settled way of carving the world into outcomes. The hardest objection, pressed most stubbornly by David Albert, is almost childlike in how it resists answering. If all the branches are equally real, and a version of me lands in every one, why should I care more about the thick branch than the thin one? Why should the sheer quantity of amplitude, a property of the wave and not of my experience, command my concern at all? The derivations reply that a consistent agent is bound to weight them so. They do not quite reply why the universe arranges for consistent agents to find themselves, almost always, inside the heavy branches, which is the fact actually seen. What I cannot set down easily is that the squared rule works without flaw in my hands, while staying contested beneath them. Our most precise prediction standing on a floor its own builders cannot agree is there. A further pressure waits, and it will come back harder. These derivations behave when the branches can be weighed against a fixed total. Let the branching run without end. Let the count of worlds climb past any finite number, and the idea of a fraction begins to wobble, since a ratio taken over an endless collection depends on how you gather the collection before you divide. The rule that performs so cleanly on any single experiment has no settled meaning once the worlds are infinite, and that same crack will split open again, wearing a different face, when the universe itself turns out to be the thing without end. The uncertainty was made to live in the gap after the branch forms, and before you read it, a person not yet knowing which copy they are. That account rests its full weight on a before and an after, on one moment that has not yet turned into the next. The equation doing all the branching holds no such moment anywhere inside it. If the only chance left in physics is the chance of which version of you the next instant delivers, then where, in an equation with no next instant, is that instant supposed to be? Write down the fundamental laws, and you can run them in either direction in time, and they hold equally well. A film of two billiard balls colliding looks just as lawful played backward as forward, and the same stays true, with one faint exception, all the way down to the equations for particles and fields. That lone exception is a small bias in how the weak force handles certain rare decays, and it is far too slight, by a staggering margin, to explain why you remember last night and not tomorrow morning. The deepest laws do not single out the direction you live through, and they carry no marker at all for the present, for the one instant you would call now. Relativity makes the absence sharper. Two events you would call simultaneous. Someone moving past you at speed would not. And no fact settles which of you is right, because the theory grants no shared present that all observers must agree on. Slice the history of everything into moments however you please, and each slice stands as valid as any other, the way a loaf can be cut at any angle without one cut being the true one. The whole of time lies laid out at once, every moment as real as every other, and the sense that one of them is lit up as the present gets added by minds rather than found in the physics. The man who built the theory wrote near the end of his life that the split into past, present, and future was a conviction he could not shake, yet understood to be only that. Two people pass on a sidewalk, one strolling toward the Andromeda galaxy and one strolling away, ordinary walking pace, nothing exotic. Relativity tilts their planes of simultaneity apart by the faintest angle. Stretched across the 2.5 million light-years out to Andromeda, that sliver widens into days. The events each of them would call happening on Andromeda at this very moment differ by days, between two strangers sharing a pavement at a walking pace. There is no third standpoint that picks the true now between them, because the physics does not hold one. The quantum equation that does the branching is, on its own, perfectly deterministic. Hand it the full state of everything at one moment, and it fixes the full state at every other moment, earlier and later, leaving no gap for chance to slip through. The only chance anywhere was the chance of which branch you wake into, and that was never the world throwing dice. It was the single word, you, handed to several people at once, each startled to learn which one they turned out to be. The law beneath stays rigid. The randomness lived only in the address, never in the machinery. Push that determinism to its edge, and something breaks in a way that has gripped physics for more than 50 years. Try to write one equation for the quantum state of the entire universe, gravity included, and the time variable falls out of it entirely. The most studied version, worked out by Bryce DeWitt and John Wheeler in the late 1960s, describes the whole universe with an equation that does not evolve in time at all, since there is no outside clock left for it to evolve against. A clock is a thing inside the universe, and the universe has no second universe beside it to be timed by. So the total state simply is frozen and complete, and the flow we live inside has to be drawn out from within rather than assumed from the start. The field calls this the problem of time, and naming it has proved far easier than answering it. One answer is quietly radical, and it earns its place. Time, on this reading, is not a stage the universe stands on. It is a relationship between the universe's own parts. Don Page and William Wooders showed in 1983 that if you take a small system as a clock and let it grow entangled with everything else, an observer who looks only at everything else, asking what its state is given that the clock reads a certain value, watches that state change as the clock value climbs. The change is fully real to anyone inside. From outside the entangled hole, nothing moves. The universe holds still, and time is the shadow that frozen correlation throws when you stand within it. In 2013, a group in Turin built a bare model of exactly this from a pair of entangled photons. To an observer reading one photon as a clock, the other photon evolved, ticked through its states, behaved as though time were running. To an observer measuring the pair as a whole, the system sat unchanging. Both readings were correct, of the same photons, in the same experiment. The passage of time switched on and off depending on whether you stood inside the correlation or outside it. Here the picture has always caught for me, because explaining the now away is a different job from explaining why it points. Grant the frozen block and the emergent clock, and one stubborn fact survives. You remember the past and never the future. A glass falls and breaks and never reassembles, though every law ruling the fragments would run that film backward without breaking a single rule. The reversibility is exact, and the one-way street is plain to anyone, and the two have to be squared inside a theory that does not, at bottom, care which way time runs. The branching squares them, and it does so with parts already on the table. Branches divide toward the future, and effectively never rejoin, for the same reason the slit stripes never came back once a witch path record existed. Once two versions of a moment tangle with their surroundings, folding them back into one lies so far past reach that it never occurs. So the count of branches only climbs. The direction you call forward is the direction in which the worlds multiply, and the arrow of time turns out to be no extra law sitting atop the others. It is the shape of the splitting itself, the same one-way tangling that hid your other selves, viewed now from the side and named the passing of time. If the laws hold no now, the flow you feel needs somewhere to live, and the cleanest place to set it is inside memory. Every slice of you, at every instant in the block, carries within it the records of the slices behind it, the half-finished thought, the sense of having just arrived from a moment already gone. A single frozen instant already contains the feeling of having just moved because it is built holding the traces of the ones before. The motion need not be real in the physics for it to be real in you. Each still frame in the block comes stamped with the memory of the frames it follows, and that stamp is the whole experience of time passing. Set the two halves together and they refuse to fight, which took me a while to accept. Seen from nowhere in particular, the block is finished, every branch and every moment fixed in place, but nobody ever stands at nowhere in particular. From inside one branch, looking ahead, the next moment stays undecided, because the fact that settles it, which version of you that instant will hold, is the one fact you do not yet carry. The whole is determined, and your next step is open, and both hold at once for the plain reason that you are a part and never the whole. So the equation lays the whole of time out at once, fixed, with the flow supplied by the records each moment keeps of the ones before it. But laying out all of time says nothing about how much space that time is spread across. The block fixes when everything is. It leaves wide open how far everything reaches. And if space runs on without end, a second kind of copy of you follows. One that needs no branching, no quantum trick, nothing but room enough. How far would you have to travel to stand in front of a version of yourself the universe simply built a second time? The copy this act reaches for needs no second rule, no entanglement, no exotic ingredient. It needs space that keeps going, and one fact about how much can fit inside a finite stretch of it. Out of those two plain things, and nothing more, a second you follows, built from ordinary matter under the ordinary laws, somewhere out in the dark. The part that unsettles is how little you have to grant before the conclusion forces itself on you. Begin with how far you can see. Light has been crossing toward you since the young universe. For most of the 13.5 billion years it has existed. So a first guess puts the farthest visible thing about 14 billion light years away. It sits far beyond that, near 46 billion, because space went on stretching while the light was still in flight, carrying its starting point steadily outward as it traveled. That sphere, 46 billion light years in every direction, is the observable universe, the full reach of everything light has had time to bring. It is not a wall, and it is not the edge of space. It is the edge of the news from the cosmos, the boundary past which nothing has yet had time to arrive. Move a galaxy to one side and the sphere recenters on you, taking in things that were hidden and losing things that were not. Because that boundary follows whoever is looking, it can only be a fact about the looking, never a feature built into the world. How far the world runs past your horizon is the open question, and the measurements lean hard one way. The oldest light in the sky, The faint warmth left from the first few 100,000 years has been mapped in fine grain, and the geometry it shows is flat to within a fraction of a percent. A flat space, in the simplest reading, has no far side to bend back to. It carries on without bound. A finite version with some exotic wrapped-up shape has not been ruled out, yet plain flat infinity is the option the data rest most easily on. Grant the endless space for a moment, because a piece of cold counting then takes over, and the counting is almost a schoolyard puzzle dressed in cosmology. Put more pigeons than holes, and some hole holds two. Run it the other way and the force only grows. Lay out an unbounded number of holes, regions of space the size of the patch you occupy, and suppose the number of truly different things one hole can contain is finite. Then not merely does some content repeat, every possible content repeats, and repeats without end, because a finite set of options poured into infinitely many slots leaves no other arithmetic available. The whole thing hangs on that one clause, that a region can hold only finitely many distinct arrangements. It sounds like it ought to fail, since you can seemingly nudge a particle by any tiny amount and call the result a fresh arrangement, an unbroken infinity of them. The reason it holds is one of the strangest results to come out of black hole physics. The most a region can record is fixed by the area of the boundary you could wrap around it, not by the volume packed inside, as though every possible state of the interior could be written on the enclosing surface with room left over. Jacob Bekenstein and Stephen Hawking pinned this down for black holes in the 1970s, and it is now thought to apply to any region whatsoever. For the observable universe, the cap lands near 10 to the 122nd bits. That figure already towers over the number of atoms in everything we can see, which sits around 10 to the 80th, so the recording capacity of the visible universe runs more than 40 orders of magnitude past the count of particles inside it. Enormous as it is, the number is finite, and a finite store of bits can be set in only a finite number of patterns, however dizzying the total. The endless slide of a particle by ever smaller steps is precisely what that bound forbids. There is a cheaper road to the same finiteness, the idea that space comes in smallest grains far below the scale of any atom, but the grain story is still a suspicion, and the surface bound does not lean on it. Either way, the count of possible arrangements settles on a number rather than an infinity, and once it does, the recurrence is no longer optional. Take that finite count seriously, and a distance attaches to your nearest exact double, the place where the arrangement of every particle around you repeats down to the last one. The estimate lands near 10 raised to the power of 10 raised to the 29th, measured in meters. The number refuses to be felt, so keep only the exponent. 10 to the 29th is how many zeros trail the leading one, and that count of zeros, on its own, already runs larger than the number of atoms in your whole body. To write down the address of your nearest twin, you would exhaust the atoms available to mark the digits long before you reached the end. The exact double is the rarest figure of all, parked at the far edge of an immense crowd of near misses. Well before you reached it, you would pass versions of you off by a single remembered detail, by one word said differently in an argument decades gone, by the seat of one atom in one cell of one fingertip. Every variation the laws permit is assembled somewhere in the endless reach, and the only thing sorting them is how far you would go to face each. The closest ones part from you in almost nothing. The distance climbs with the size of the difference. These doubles are nothing like the branches from earlier. A branch is walled off by entanglement and can never be reached by any signal or any journey. A distant double sits in the same space you do, under the same laws, divided from you by plain distance and nothing else. A long enough trip lands on it in principle. Even if the trip would outlast the universe you could make it in. The quantum copies are pressed right against you and permanently out of reach. These others are unthinkably far and, in the barest theoretical sense, simply somewhere down a road. Pull either leg from under the argument, and it folds. If space proves finite, however gigantic, the repeats are never compelled, since a finite room runs out of arrangements before it runs out of room. If space is smooth without limit, and the surface bound somehow fails, a single region could carry endless detail, and nothing would ever be forced to recur. So, the copies are not a finding, they are a consequence, set on two premises we hold for good reasons and still cannot confirm, and that is the honest weight of the claim. Every double and every near miss leans on one demand, the same one, and it is the demand most easily mistaken for something smaller. A merely colossal universe will not do the work, because a finite space, no matter how immense, exhausts its arrangements before each one has had its turn. The copies require space that is not just vast, but actually without end. So the whole picture rests on the question of how a thing could ever have come to be infinite in the first place. What poured out that much space, and is there any reason to believe the pouring ever stopped? Run the clock back far enough, and you reach a stretch when space did not expand so much as detonate. In the first unimaginably brief instant, a patch of the infant universe doubled in size, then doubled again, and kept doubling on a clock ticking faster than anything since. This is inflation, and Alan Guth set it down in the early 1980s to fix two problems no one could otherwise explain. By the time it ended, in less than a trillionth of a second, that patch had grown by a factor of at least 10 to the 26th, enough to swell a region smaller than a single proton up to roughly the distance from here to the Sun. The first problem it solved was the sky's strange sameness. Look in opposite directions, at patches so far apart that light has never had time to pass between them since the beginning, and the leftover heat from the early universe reads the same temperature in both, matching to 1 part in 100,000. Two regions that never traded a signal should have no reason to agree on anything, yet they agree almost perfectly. Inflation explains it by saying the patches were once tucked close together, in easy contact, before the runaway expansion flung them to opposite ends of the sky in an eye blink. The uniformity is the fingerprint of a closeness that came before the stretching. The second problem was the flatness from the last act, the geometry that sits balanced on a knife edge. Stretch any surface violently enough, and it flattens. The way the skin of a balloon grows less curved, the larger you blow it. Inflation flattens space the same way, which is why the curvature we measure sits so close to zero. The engine driving all this was a field-filling space with energy, and the part that breaks intuition is how that energy gravitated. In general relativity, gravity does not answer to energy alone, it answers to pressure too, and a field of this kind carries a pressure so strongly negative that it turns gravity inside out. Instead of pulling space together, it shoved space apart, harder the more space there was. The burst ended when the field slid down to a lower energy and dumped everything it had been holding into a flood of hot particles, the searing start we usually call the Big Bang. So the Big Bang was not the beginning of the engine. It was the moment the engine switched off in our patch and handed its energy to matter. What lifts inflation above a tidy story is that it left a signature, and we have read it. The same field that drove the expansion could not sit perfectly still, because quantum fields never can. It jittered, and inflation stretched each jitter to enormous size, freezing a faint pattern of denser and thinner regions across the sky. Those frozen ripples became the seeds that gravity later grew into galaxies. The pattern carries a precise tell, a slight unevenness across scales rather than a perfectly uniform one, leaning by a few percent in exactly the direction simple inflation predicts. Every galaxy, including the one you are lying inside, traces back to a quantum tremor blown up to span the heavens. The structure of the cosmos is an old piece of quantum noise, enlarged past recognition. Now, the turn that makes this an act about copies rather than cosmology. The field does not switch off everywhere at the same time. Because it jitters, Some regions linger high and keep inflating while neighboring regions drop out and cool into ordinary universes like ours. And inflating space, by doubling, manufactures new inflating space far faster than the dropouts can drain it away. The total inflating volume never falls to nothing. It grows without end, budding calmer pockets inside itself forever, each pocket a full universe in its own right. This is eternal inflation, worked out by Andrei Linde and Alexander Vilenkin, among others in the 1980s. And the word eternal points forward, not back. Once the process starts, no global moment ever arrives when all of it has stopped. Each pocket that drops out can freeze with its own low-energy rulebook. The way the field finally settles can leave particles with different masses, forces with different strengths, perhaps a different count of dimensions left large enough to matter. These are not far-off regions of our own space, the way the doubles from the last act were. They are separate universes running on separate physics, sealed off because the space between them keeps inflating faster than anything could ever cross it, and the scales now stack in a way worth holding steady. Everything from before, the whole observable universe, the endless flat space past our horizon, every distant copy of you scattered across it, all of that fits inside a single one of these pockets. Each pocket may itself be infinite, and there is no end to the pockets. Infinities seated inside a larger, boiling infinity. Press back toward the start, though, and the theory goes quiet in an honest way. For a while it was hoped inflation might reach back forever, needing no beginning to account for. A result by Arvind Borde, Alan Guth, and Alexander Vilenkin in 2003 closed that door. They showed that any universe expanding on average the way ours does cannot be stretched into the infinite past, that any history you trace backward must run out at a true edge somewhere behind the inflation. What sits at that edge, and whether anything at all preceded it, the mathematics hands back without an answer. There is a quiet trap in even asking, and it took me a while to see it. We reach for the word before as though it must point somewhere, as though there is always an earlier to find. But if time itself only takes shape together with space, then before may have no place to land, the way a road that ends at the shoreline does not continue underwater simply because you were still walking. The question of what came first might not be hard so much as built wrong, and telling a hard question apart from a malformed one is itself one of the open problems, not a step on the way past them. With every pocket free to set its own constants, the great majority come out lifeless. Nudge the strength of a force a little and stars never light, or matter never clumps, or atoms never hold together long enough to build anything. The overwhelming run of these universes are sterile and dark, and the rare hospitable ones are hospitable by accident, not by design, the few draws that happen to land in the narrow band where chemistry and structure are possible at all. So the machine runs without end, minting universes past counting, most of them empty, a scarce few of them warm, and once you have endless pockets and endless time, a colder thought follows on its own. Anything that can assemble itself by sheer chance will assemble, somewhere, not once but again and again. If reality has forever to keep rolling, then a fully formed mind, complete with a lifetime of memories of things that never happened, is not ruled out. It is merely rare. So what reason do you have, lying here, to trust that the past behind you tonight ever actually took place? The reason you can lean on a memory at all comes down to a single feature of how everything began. The early universe was almost perfectly smooth, the same density and temperature in every direction, to within a few parts in 100,000. Smoothness sounds like the very picture of order, and for most things it would be. For gravity, it runs the other way. Gravity pulls matter together, so an even spread of it is the loaded, unstable setup, packed with the potential to collapse into stars and galaxies, while the clumped and lumpy state most people would call messier is the one gravity scores as run down and high in entropy. The universe opened in that loaded state, and everything since, every star lit, every structure raised, every flow of heat from hot to cold, has been the slow cashing in of that first reserve of order. That one-way spending is where your memory comes from. A record can be laid down and held only because the universe still has order left to spend. A hill it has not yet finished rolling down. Carry the slide all the way out, and it ends in stillness. Stars burn through their fuel, matter decays, and the largest black holes evaporate after something near 10 to the 100th years, a 1 trailed by 100 zeros, set against a universe still under 14 billion years old. What is left is a thin, cold, even haze at one temperature throughout. The state of maximum entropy, with no gradient anywhere to drive an event or keep a memory. The smooth beginning and the smooth ending look almost identical, and only the gravity sorts one from the other. Which leaves a question physics has never closed. Why did it begin so ordered? A low entropy start is absurdly special, one arrangement drawn from a pool of disordered ones so vast that counting them defeats any notation we have. Dropped down at random, a universe should have been born already spent, flat and dead, holding no reserve and no arrow of time at all. Ludwig Boltzmann, the man who first tied disorder to probability, saw the trouble in the late 1800s. If disorder is the default, and time runs long enough, then order is not a rule but a rare accident, a chance dip that briefly lowers the entropy of some patch before it slumps back into noise. He wondered aloud whether the whole ordered world might be one such fluke, flickering inside an otherwise dead and shapeless eternity. The arithmetic of flukes is what makes the thought dangerous. A small dip in disorder is overwhelmingly likelier than a large one, and the gap between them races past comprehension as the dip grows. So, if you are the product of a chance fluctuation, the cheapest version of you, the one needing the least improbable dip, is not a whole person inside a whole galaxy with billions of years of real history behind it. It is the barest scrap of order that can carry an experience, a single brain assembling for one instant, stocked with a complete set of memories of a past that never happened before coming apart again. These flickers carry a name, Boltzmann brains, and the cold count says they should outnumber observers like you by a margin with no floor. A coherent universe is the most expensive fluctuation imaginable, and a lone, diluted brain is nearly the cheapest one going. By the numbers, you ought to be one of the cheap ones. What lifted this from a curiosity to a live worry was the discovery that our universe is not winding down toward emptiness, it is accelerating into it. A space pushed apart by a constant energy drifts toward a state with a faint horizon warmth of its own. A temperature measured at a decimal point followed by 29 zeros and then a 1, in degrees above absolute zero. That warmth is almost nothing, and almost nothing acting across a literal forever still adds up. In an eternal accelerating space, brains do fluctuate out of the vacuum, on timescales written as 10 raised to the power of 10 raised to the 50th years, a tower so tall that the 100 to 0 heat-death figure shrinks to a rounding error beside it. Finite waiting, endless time, and the freaks keep arriving. The way out does not come from calling the conclusion unbearable and turning away. It comes from holding the idea against what you actually see. A brain fluctuated out of chaos has no reason to find order anywhere it looks, since the same randomness that threw it together would pack its surroundings with noise. Look across the room and find it coherent. Set one clock beside another and find them keeping step. Run a measurement twice and draw the same result, and you are seeing precisely what a random mind should almost never see. The consistency you keep uncovering is the evidence itself. A real, lawful universe predicts that your next look will hold together, and the prediction keeps coming true. A freak fluctuation predicts that your next look should crumble into noise, and it never does. Cosmologists have hardened this into a tool for throwing out theories. Any model of the universe that ends up predicting mostly Boltzmann brains is treated as broken, not because the answer offends anyone, but because it cuts its own evidence away. If the typical observer in your theory is a deluded flicker, then the observations you built the theory on were likely delusions too, and the theory dissolves the very ground it stood on. More than one otherwise serious cosmology has been set aside on exactly that charge. The relief is real, and it is also on loan. Whether the freak minds truly outnumber the rest hangs on how you count observers spread across an infinite universe, the same measure problem that left the quantum branches uncountable and the distant copies impossible to weigh. Until that counting is settled, your reason to trust the past you remember rests on a wager, a strong one that the orderly world keeps paying out, but a wager all the same. What strikes me is the dullness of the evidence that keeps you sane. The one thing standing between you and the suspicion that you assembled a moment ago is the plainest act there is, looking twice and finding the same thing both times. The deepest assurance on offer comes dressed as the most ordinary glance. And the order is not only out in the early sky, it is the thing holding you together at this moment. Every thought you keep steady is paid for in heat. To stay a low-entropy pattern, your body survives only by exporting its disorder, handing warmth to the air, sending waste outward, shedding the heat now leaving your skin into the dark. The memories you are resting on tonight are physical patterns, held in the standing structure of your brain, and they keep their shape only because the universe still has order enough to let a pattern hold. You are running the same downhill spin that began with the smooth early cosmos, slowed to the pace of one quiet body keeping itself whole for another night. But the whole frightening argument leaned on one move nobody examined. It took for granted that a brain is the sort of thing that can simply fall into place, and that once the arrangement exists, the experience comes with it for free. Not once did we stop to ask whether arranging the matter correctly is really enough to switch a mind on. What has to come into being before there is anyone there at all? Run a careful tally of the matter in your body and most of it is on its way out. The atoms get traded for fresh ones drawn from food and water and air, cycled through and swapped over months and years while the shape of you carries straight on. The neurons are a striking exception, and the exception sharpens the point instead of softening it. Carbon dating of brain tissue has shown that most of the neurons in your cortex are as old as you are, never replaced across an entire life. And even so, the atoms inside those lasting cells turn over without pause. So even the parts that endure are enduring as patterns, not as particular stuff. The cell keeps its form while its material pours through. The way a candle flame holds one steady shape while the matter burning inside it is replaced from one instant to the next. You are not the matter. You are the arrangement the matter is briefly pressed into, a form that outlasts any of the atoms tracing it by decades. Your brain runs on something like 86 billion neurons, close to the count of stars filling the Milky Way, wired together by somewhere between 100 and 1,000 trillion connections. Count those connections off one per second, and you would still be counting after 3 million years. We have mapped the complete wiring of a roundworm, all 302 of its neurons, finished back in the 1980s, and only last year the full wiring of a fruit fly, near 140,000. The human pattern is larger than the flies by something like 1,000,000 times over, and it is that web, not the atoms threading it, that the word you has been pointing at the whole time. A machine records the exact arrangement of every particle in you, ships the blueprint across space, and builds a faithful version from new atoms at the far end while the original is taken apart in the process. The one who steps out at the other side remembers your whole life and is certain it is you. On the pattern view, it is right, because nothing that made you yourself was lost, only the particular atoms, which were never the point. Now run the same machine and skip the last step, leaving the original standing. Two of you walk away, each carrying the same history, each equally sure of being the real one. There is no hidden fact underneath that crowns a winner, no private thread of true selfhood that left with one and not the other. because the only thing either one ever was is the pattern, and the pattern is now running in two places at once. If you are the pattern and not the matter, then the distant double out in the endless space was never a copy of you. It was you. A second real instance of the same arrangement, no less you than the version lying here in the dark. The branches that split off near the start were not other people wearing your face either. Each one held a full claim to your name the moment it formed, the word copy, which has carried quietly through every act so far. Turns out to have been the wrong word from the beginning. There is no original anywhere to be a copy of. You do not feel like an arrangement that could be printed twice. You feel like one unbroken person, pulled along a single thread from waking to sleep. But hunt for that thread, and it comes apart into the same mechanism from the act on time. Each moment of you holds the records of the moment just before, stitched into a sense of continuity that needs no extra substance to exist. The self that wakes tomorrow is simply the one that remembers being you tonight, and a duplicate would pass that test every bit as cleanly. Every step here has explained what the pattern does, how it stores, how it reports, how it carries on, and not one step has explained why any of it is felt from the inside. In 1974, Thomas Nagel asked what it is like to be a bat, and the question was never about how bats behave. It was about whether there is anything it feels like, from within, to be one at all. 2 decades later, David Chalmers gave the gap its name, the hard problem, the chasm between describing a system that processes and reacts and accounting for why there is an inner light on while it does so. A process could carry out everything a brain does in total darkness, inputs turning into outputs with nobody home, no taste of red, no sting of cold. That there is something it is like to be you, rather than nothing at all, is the one fact the pattern story cannot reach, and science holds no agreed answer to it anywhere. If experience truly rides on pattern alone, the stuff carrying the pattern should not matter. Neurons, or silicon, or some arrangement no one has built yet, all of them ought to hold the same mind, so long as they hold the same web of relationships, the way a melody stays itself whether a piano or a violin plays it. Chalmers pressed this with a careful argument. Replace one neuron with a silicon chip that does exactly the same job, then another, then all of them, and if your behavior never changes, then either your inner experience quietly vanished along the way, which would be bizarre to go unnoticed, or it rode across the swap untouched. The second reads as far more believable, and it points straight at a mind that depends on the pattern and not the meat. This was the unexamined bet folded inside the freak brain argument from before, the silent assumption that arranging the parts correctly is enough to switch experience on. The bet is not settled, and the sharpest challenge to it comes from a theory that takes consciousness seriously enough to put a number on it. Giulio Tononi's integrated information theory ties experience not to what a system computes, but to how tightly its parts weave their causes together, and it reaches a startling verdict. A digital machine could reproduce every output of your brain, pass for you in any conversation, and still, by this account, have almost no experience at all because its causal architecture is laid out flat where yours is deeply interlocked. If that theory is right, the pattern alone is not enough, and a perfect simulation of you would be a convincing dark room with no one inside. Nobody knows whether it is right. The disagreement runs straight through the question of whether you could ever truly be copied at all. Try to ask which of the two copies you would wake up as, and watch how fast a certain answer arrives, how strongly it feels there must be a fact about which one is the true you. Then watch that feeling reach for something the physics simply does not contain. The certainty is real, and the fact it grasps for is not there, and sitting with that mismatch, refusing to force it shut, comes closer to understanding what a self is than any confident answer would. So you may be a pattern, a structure that matter only carries for a while, the same structure able, in principle, to run in more than one place. But if what you are is finally a web of relationships, rather than any particular stuff, then it starts to look less like a physical object and more like something that could be written down in full. Does a structure like that have to be built and set running for there to be someone there? Or is a complete enough description of it already, in some sense, the thing itself? Sometimes the mathematics gets to the destination before any observation does. In the 1860s, James Clerk Maxwell wrote down a handful of equations tying electricity to magnetism, and when he combined them, they predicted a wave that traveled at one fixed speed. The speed came out equal to the measured speed of light, and the equations were quietly telling him what light was before anyone had set out to ask. The same thing happened again a century on. Murray Gell-Mann sorted the known particles into a pattern built from pure symmetry, and the pattern left one slot empty, demanding a particle nobody had seen, with a mass and a charge the symmetry fixed in advance. A few years later, that particle turned up in a detector, landing on the predicted numbers. Reality keeps being found waiting at the end of a calculation, holding exactly the object the math insisted had to be there. Eugene Wigner gave the discomfort a name in 1960, calling it the unreasonable effectiveness of mathematics. The strange part is not that math describes the world. A language good enough to describe anything would describe the world too. The strange part is that it leads, naming things no measurement hinted at, and being right. You can read that as a lucky accident, a tool we sharpened against the world until it happened to fit, or you can read it as a clue about what the world is actually made of. The boldest reading was pushed furthest by Max Tegmark, and it is short enough to state in a breath. Physical reality does not merely obey a mathematical structure. It is one, a particular web of relationships that we happen to inhabit from the inside. On this view, the equations are not a description laid over the world. The equations are the world, and the solid feel of matter is only what it is like for one part of the structure to register another part it is bound to. The structure does not need a substance underneath to be made of. Being the structure is all there is to it. Nothing marks our particular structure as special among all the others that hang together just as consistently. So, every consistent structure should exist in exactly the sense ours does, each its own universe, with its own laws, its own logic, perhaps its own kind of time, or none. This is the last and widest level. The reason there is more than one world is no longer extra space or extra inflation. It is that there is more than one way for mathematics to be consistent, and reality withholds existence from none of them. If you are, at bottom, a structure, then on this view, you are not a fragile structure haunting some realer material. You are as real as anything ever gets, because being a consistent structure is the whole of what existing means, and the atoms were never the solid thing beneath you after all. The flame keeping its shape was not borrowing reality from the wax. It was the shape that was real, and the wax that came and went. The same suspicion arrives from a wholly different direction, out of the search for one final theory. String theory set out to be exactly that, the single bedrock equation that would pin down every particle and force with nothing left free to choose. Instead, when physicists worked through the ways its extra dimensions could curl up, they found not one answer but a forest of them. The figure first quoted was 10 to the 500th, and later, counts of the geometries ran far higher still. To feel that size, you could give every one of the 10 to the 80th atoms in the visible universe its own private universe, then give every atom inside each of those its own universe, and repeat that nesting several times over before the tally was spent. Each curling yields a universe with different particles, different forces, different constants. Whether that forest is a map of real worlds or a symptom of a theory gone slack is one of the open fights in physics. One camp reads the landscape as the concrete territory of the earlier levels, every curling realized as an actual universe. Another reads it as a warning, a theory so loose it can fit nearly any observation and so predicts nearly none, which in physics sits a short step from saying nothing at all. A sharper response has come from the Swampland program, which argues that most of the theories that look consistent on paper secretly cannot be completed into a full theory of quantum gravity and belong to a swamp of imposters rather than a landscape of real worlds. If that holds, then consistency is far harder to earn than it appears, and the casual leap from describable to genuinely possible loses its footing. The landscape may be the strongest case yet for a multiverse, or the strongest sign that a wrong turn was taken, and from inside our one curling there is no way yet to tell which. What makes me wary of the mathematical universe is the very feature that makes it powerful. It cannot be cornered. Any world you can describe without contradiction, it has already swallowed, so no result you could ever record would count against it, and a theory that forbids nothing carries a peculiar emptiness even where it might be true. It wins every argument by containing every answer, and it teaches you nothing about why you woke into this world and not one of the countless others it grants equal standing. A picture that explains all outcomes explains no particular one. Taken on its own terms, the idea strains where every level before it strained. To say all structures exist equally invites the measure problem one more time, with no way to weigh an infinity of universes against each other, and no rule for what you should expect to find yourself inside. And it leans on a notion that may not even be coherent. There is famously no set of all sets, no clean totality of everything mathematical, and a structure rich enough to hold conscious beings is likely rich enough to fall under exactly the limits Kurt Gödel exposed, where no system can fully capture its own truths. Tegmark himself later tried to retreat to only the computable structures to steady the ground, which trims the claim but does not close the seam. Press on that seam, and the floor under the whole tower thins. Grant that all consistent mathematics exists. You have still said nothing about why there is any arena in which mathematics gets to be real at all, why consistency should ever cash out as a world with someone awake inside it, rather than staying a set of dry truths with nobody anywhere to register them. The mathematical universe tries to dissolve that worry by defining existence as consistency, but naming a problem out of the way is not the same as answering it. And underneath the cleverest version of the idea, the oldest question there is sits exactly where it always sat. So 4 kinds of endless worlds have brought us down to a foundation made of nothing but structure, a reality that is pattern all the way through with no stuff beneath the pattern. And yet the structure being consistent does not seem to be the same as the structure being lit, being present, being lived from inside by anyone at all. Why should a description, however complete, ever be more than a description? Why is there any structure switched on and awake, rather than the bare possibility of one and nothing more? Take the emptiest space physics allows, colder than anything, and swept clear of every particle, and it still is not nothing. 2 polished plates set a hair's breadth apart inside that emptiness will drift together on their own, pushed by a pressure with no particles behind it to do the pushing. Hendrik Casimir worked the force out in 1948, and the labs have measured it since. The push comes from the quiet fields that fill all of space, even after everything removable has been removed. And on paper, that quiet is alarmingly loud. The theory's tally of energy in empty space runs larger than the measured value by a factor, with about 120 zeros trailing it. Set that beside the roughly 10 to the 80th atoms in everything we can see, and the atom count disappears into the error bars. No prediction in the history of physics has ever missed by so much, and it means the inside of that empty space is far less understood than the precision of the experiments makes it look. The vacuum of physics is not the absence of everything. It is fields resting at their lowest energy, governed by laws already running, inside a space and time already laid down. The stage is built and lit. It simply has no actors standing on it. So when someone says a universe could spring from nothing through a chance fluctuation, weigh what that word nothing is quietly holding. Underneath it sit real quantum fields, the rules they follow, and a space-time for them to ripple inside. That can be a real account of how a universe gets started from within physics. It says nothing about why there is any physics to start from. The nothing the old question points at is far more austere than any vacuum. Strip away the fields, the laws, the space-time, the empty stage and all, until not even the possibility of an event remains. Out of that, nothing can fluctuate, because fluctuating takes both a thing to do it and a rule that allows it. Every from-nothing story makes the same quiet substitution, setting the easy nothing where the hard one was asked about, and explaining the easy one, which is how the hardest question keeps seeming solved while only being swapped for a smaller one wearing its name. Each tier answered the question why this way by replying that every way happens, somewhere. Which outcome, which arrangement of matter, which constants, which laws. Every one of those took the same dissolving answer, that the alternatives are all real too. None of the tiers reach the question beneath them, why there is a somewhere for any of it to be, why being at all rather than its absence. Piling on more worlds enlarges what there is. It never reaches the fact that there is anything. And each tier sat tucked inside a larger one, so that pointing to any final container only raises the same question one layer out. What contains that? Either the containers fall away beneath you without end, or one of them has to be the kind of thing that needs nothing under it. Gottfried Leibniz set the question down plainly 3 centuries ago, and it has not shifted since. 3 replies get offered, and each one buckles. The first calls existence a brute fact, true for no reason at all, which closes the conversation without ever meeting it. The second says a true nothing could not have held, that absence is somehow unstable and being had to break out of it, except that an instability is already a rule, a sliver of something slipped in to outlaw the nothing. The third says the question is broken, that the word why has wandered past the last place it can stand, and that may be so, though it sounds uncomfortably like surrender dressed in the clothes of insight. Out of every question this night raised, this is the lone one I have never watched anyone shift. In all the centuries it has been asked, and there is an odd steadiness in admitting that out loud, rather than dressing the silence as an answer. The rest of the night's puzzles give a little when you press them. This one returns your weight and stays exactly where it was. And the missing floor reaches up to you as well. If nothing anywhere can say why there is anything, then no reason is on file for why you in particular are here. No justification that was ever owed or could ever be produced. The equations did not call for you. You arrived with no reason the universe can name, and whether that lands as the bleakest fact imaginable or the most freeing one turns wholly on what you make of a life that came with no terms attached. So set the infinite down, since it was never yours to hold. Look instead at what is moving in the dark around you. Your body is shedding warmth into the room, infrared light slipping off your skin into the cooler air, and each photon that leaves takes with it a trace of exactly where your body was when it left. That slow loss of heat is the sealing from the start of the night happening inside you, the entanglement that closes one branch off from all the rest. By the time you finish drawing a single breath, the you who drew it has been cut off from every other you far more completely than any gulf of distance could manage. This was meant to be the crushing part. If every choice you might make is taken by some version of you, the worry runs, then your choices wash out, lost in an endless book where everything occurs and so nothing weighs anything, each act smeared so thinly across so many worlds that it thins away to nothing. The ceiling turns that on its head. Because the branch you are in is shut, your act is not smeared across infinity at all. It stays undivided, here, with no other version anywhere to take a share of it and nowhere else it could come to rest. And since every branch is fully you, the worse self off in some other world is no excuse that lightens this one, because that self owns its branch as completely as you own yours. Nothing trades across the gap between branches. So no kindness in a world you will never reach can be set against a harm done in this one. Every branch closes its own books, by itself, in the hand of the one person living inside it. The empty floor under the why question folds into this too, with no reason anywhere for why anything exists. There is no scorekeeper outside your branch totting up the worth of your night. No figure above the world handing it a value. The cosmos grants your choice nothing from the outside, and that very absence is what leaves the worth of it to be fixed from the inside, by the one doing the fixing. A world with no ground is not a world where nothing counts. It is a world where what counts gets settled here, in this room, and in no court above it. Every piece of physics that carried this night is at work in you right now, only pitched down to the scale of one body. The splitting of worlds, the slow downhill spend of order, the restless fields crowding the space your chest pushes through, none of it is kept for the distant stars alone. It is running the breath moving through you, the warmth held under the blanket, the bare fact of your being here to follow any of it. You never had to reach for the infinite to touch the physics. It has been keeping you company in the dark the whole time. So here, at the end of the long way out and back, there is nothing for you to carry into sleep. The infinite was never a weight you were asked to lift, and not one of your other selves, near or unthinkably far, has any claim on whether you stay awake tonight. The opening of the night asked what could still be only yours, with so many versions of you scattered through the worlds. The answer turned out to be the smallest thing imaginable, and the only one that matters. The single branch your warmth is quietly sealing around you, right now, in this room, is the one your hands will ever actually reach, and that is what makes it wholly and only yours. Thank you for going the whole distance, out past every horizon, and back down into one warm, ordinary, particular dark. There is nothing more to understand tonight, and nothing left to settle. Let the warmth go where it is going. Let the breath find its own slow rhythm without you steering it. Whatever the worlds are doing out past the edge of this one, they will go on doing it perfectly well without you for a while. Rest now. Good night.